Hello students, let us look at adjoint of a matrix. This is a new concept. Now how do we define an adjoint? For any square matrix A, adjoint of A is defined as transpose of the matrix obtained by replacing all the elements of matrix A by their cofactors. In short, the transpose of the cofactor matrix is adjoint of a matrix. Let us look at it with an example. Suppose A is a matrix of the order 3 by 3, that is A11, A12, A13, A21, 2223, A31, A32, A33. Now, the cofactor of matrix A will look like this, that is C11, C112, C13, up to C31, C32, C33. That is, the cofactor of element A11 will be C11. Similarly, the cofactor of element A23 will be C23. Now, this is the cofactor matrix. Now, students, adjoint of A is defined as simply taking the transpose of the above matrix. That is simply taking the transpose of the cofactors. The cofactor taking transpose, the adjoint A becomes C11, C21, C31, C12, C22, C32, C13, C23, C33. That is simply we have taken the transpose of the cofactors. Let us try to find an adjoint of a matrix of order 2 by 2. Now, A, B, C, D. We know how to find the cofactors. C11 will be the cofactor of A11, that is minus 1 to the power I plus j, and determinant of the elements obtained by removing the corresponding row and column, that is D in this case. So C11 will be D. Similarly, C12 will be minus of C. C21 is minus of B, and C22 we get as A. Now, if we take the transpose of the cofactor matrix which is formed, the adjoint A will be transpose of D minus C minus B and A. So we get transpose of matrix A, or the adjoint of matrix A, as D minus B minus B, C and A. There's an important point to be noted here. To find the adjoint of a 2 by 2 matrix, we just notice that we just have to exchange the diagonal elements and change the sign of the rest of the elements. So in this case, A and D have to be exchanged. So A gets in the place of D, D gets in the place of A, and all the other elements gets minus sign. So this is how we can easily find the adjoint of a matrix A, which is of the order 2 by 2. Now, this is an important property of adjoint. A into adjoint A, if we try to find out the product A into adjoint A, we get these two get multiplied and we get this very matrix, that is A11 C11 plus A12 C12 plus A13 C13 and so on. Now, when we multiply A with adjoint A, we see that the diagonal elements, they're simply different forms of writing determinant of A, that is multiplying the elements with the corresponding elements of the cofactors. So if we look at the element which is A11 C11, A12 C12, A13 C13, this is multiplying the first row with the first row of the cofactor. Similarly, A2 is multiplying second row of the matrix A with the second row of the cofactors, which gives us determinant. Similarly, A33 is determinant of A, multiplying third row of the elements with the third row of cofactors. While the other non-diagonal entries, this is simply multiplying elements of one row with the corresponding cofactors of another row. Hence, the non-diagonal elements are all zero. Let us look at the element in the first row and the second column. This is A11 C21, A12 C22, A13 C23. That is, first row of the matrix is getting multiplied by the second row of the cofactors. In this case, second column, because this is adjoint of A and not cofactors. But A11 C21, A12 C22, A13 C23 is first row of the matrix with the second row of the cofactors, which gives us 0. So this element is 0. Similarly, all the non-diagonal elements are 0 in this case. So diagonal elements are all determinant of A. and non-diagonal elements are 0. So A adjoint A becomes matrix determinant A 0 0 0 determinant A 0 0 0 determinant of A. If we take out determinant A as common, this becomes determinant of A into identity matrix of order 3. This, students, is very important property of adjoint. That is, A into adjoint A is determinant of A into I. A into adjoint A can be written as determinant of A into I, and this can again be A into adjoint of A n.